Now, in this lecture, I'm going to talk about the atomic force microscopy. Now, since the introduction of the Nobel Prize-winning scanning tunneling microscope in 1981, I think, and then the invention of atomic force microscopy is again a landmark invention of the same STM inventor, Binning, and with another scientist. So they brought this idea into limelight, which they can use ultra small probe tip at the end of a cantilever. Why they wanted this is because the scanning tunneling microscope, even though it has high resolution, that technique is limited to use only conducting samples with conducting metal tips. But if you have an unconducting materials, then you need to find another way. That's why they were looking into this atomic force microscopy, right? So in 1987, a Sri Lankan scientist, Wickramasinghe, and his group developed this AFM setup with the vibrating cantilever technique, which nowadays we use this light lever mechanism to image. It was introduced added to the AFM by this group. If you want to go and check the publications, it is available in Journal of Applied Physics in 1987. Yeah. So in the atomic force microscopy, they in the Bing, Koch, and the Gerber. These are the scientists. They invented this AFM in 1985. The original AFM consisted of a diamond shard attached to a strip of gold foil, and diamond tip contacted the surface directly, and with the interatomic van der Waals forces, it gives the interacting mechanism. And detection of the cantilever's movement was done with the second tip, an STM placed above the cantilever. So this basically what happens here when you bring the cantilever tip closer to the sample, there will be van der Waals forces, magnetic forces, atomic forces, likewise so many forces that will mechanically tilt the tip. So the tip position, originally in the original invention, it was detected by another STM tip. But then in 1987, Wickramasinghe's group invented this light lever mechanism. Right. So in the light lever mechanism, they use a laser and a photodiode array. Right. Traditionally, most AFM use a laser beam deflection system where the laser is reflected from the top of the tip and is directed towards a photosensitive detector, which consists of photodiodes. Right. High sensitivity for detection at 2 dimensions. Then AFM tips and cantilevers are typically microfabricated from silicon or silicon nitride. Typical tip radius, this tip radius is from a few to tens of nanometers, right? Because the atomic force microscope relies on the force between the tip and the samples, these force impact AFM imaging. The force is not measured directly, but it is calculated by measuring the deflection of the lever given that we know the stiffness of the cantilever. So you know the Hooke's law, very famous, F equals minus kz. Okay, Z, K is the stiffness of the lever, Z is the distance, how much the lever is bent, and F is the force. You can calculate the force using this Hooke's law. So this photodiode consists of, like, it's a 4-quadrant photodiode. You have A, B, C, D here. The movement, normally when there's no force, it is focused onto the center of this photodiode array. Let's see how it works in the next slide. Laser sensing to monitor the position of the cantilever. We have basically 2 modes, contact mode scanning and non-contact mode scanning. In the contact mode scanning, cantilever is usually not vibrating, but deflected due to the friction or other forces that act on the cantilever. Such deflection can be detected precisely by the sensitive photodiode. In non-contact mode scanning, cantilever does not directly touch the sample, but cantilever is in vibration with a constant frequency, and such vibrations also precisely monitored by the laser sensing. Now, to keep the resonance frequency or the constant height of the sample during the scanning, what happens, the Z scanner has to adjust the height of the cantilever. Such adjustment will be recorded by the computer and create the scanning profile of the image. So when now the tip is resonated at a resonating frequency, when the distance is changed, the force magnitude is different. Now, if it is like, if there's a step, cantilever gets closer, atomic forces are more prominent, then the vibration is now changed. That change can be monitored. If there is a dip, the tip to the sample distance is increased, then there is a change. I mean, because of that change in the distance, there's a change in the force and the change in the deflections, cantilever vibrating frequencies. These changes are all recorded and will be used to create the scanning profile of the image. So laser sensing for both tilting and twisting of the cantilever, I mean, these deflections can be either tilting or twisting. If it is like tilted, that means it's move up and down. That means the this laser patch or the reflected laser light is if it is going between AB, it is up, or if it is going between CD, it is going down. This is going down, so that is tilting. Twisting means it's the lateral forces. So in this case, the twisting will move the reflected laser light either left or in the right way. So if it is moved towards the A and C, that is its left, and if it is moved towards the BD, that is it is shifted to or twisted to right direction. So how to create a vibration cantilever? There are 2 ways to drive the cantilever into oscillation. One way is accomplished by indirect vibration, in which the cantilever is excited by high frequency acoustic vibration from a piezoelectric transducer attached to the cantilever holder. So we call it acoustic AC mode. Another more favored method is much cleaner and gentler than this AAC mode. It is the direct vibration method, where the cantilever is excited directly without having to vibrate the cantilever housing or any other part. So we directly excite the cantilever. This is called the magnetic AC mode. To achieve the magnetic AC mode, imaging cantilever coated with a magnetic material is driven into oscillation by AC magnetic field. So we get the tip, we cover it, we coat it with a magnetic material, and we have that AC magnetic field. So AC magnetic field means its amplitude is changing. So depending on the AC magnetic field, the tip is oscillated. So we don't need to vibrate the whole housing of the cantilever. We just only shake or vibrate the cantilever. Now, this AC magnetic field we usually generate by a solenoid positioned close to the cantilever housing. So this MAC mode, it's a gentle, clean cantilever response can be extracted, and it does not have any like background signals like noise. It's like it appears like forest of peaks, like in the other acoustic AC modes. So MAC mode is much more reliable and can be easily used when we use it in liquid. Right, so this is a schematic diagram. You have the sample here, you have the cantilever with the tip attached to it, and laser is pointed towards the AFM cantilever, and the reflection is now positioned on the center of the 4-quadrant photodetector. So we lower the cantilever tip towards the sample and then starts scanning it, raster scan it in X, Y direction, and depending on the atomic forces interact on this tip, that will make the cantilever tilt and twist, and these are all recorded by the 4-quadrant photodetector. Now we'll see what are the available atomic interactions. So here when we have when the tip is far away from the surface, it is out of the feedback loop because the distance is too great. The atomic forces does not have any impact on the cantilever tip. So we keep on lowering the tip, then we come to this attractive region, or we call it the non-contact mode. Here the tip is pulled towards the surface. And then what happens? Then we keep on lowering the tip, and we bypass that attractive region and we come to the repulsive region, where we call it the contact mode, and there the tip is repulsed. Now it's too close, it repulses the tip. We will see why there's a repulsive regime and attractive regime depending on the tip surface distance. Now this repulsion is due to because there's very small tip sample distances, probably few angstroms, a very strong repulsive force appears between the tip and the sample atoms. The origin is so-called exchange interaction due to the overlap of electronic orbitals of at atomic distances. So the atomic the electrons density of the atoms in the tip and the electron density of the sample, they overlap, and electrons in both sample and tip atoms, they have negative charges, therefore they start to repel each other. So if you try to move them closer and closer, what happens? Because we don't bias them, there's no tunneling current here, it's just they try to repel each other. So when this repulsive force is predominant, the tip and sample, we consider them to be in contact, because actually the electron electron orbitals are now overlapping. Basically it is like touching, not physically, like because the electron orbitals are overlapping, we call it it is in contact mode. In the attraction region, what happens? The polarization interaction between atoms. So there will be an instantaneous polarization of atoms, induces polarization in nearby atoms. Therefore, it becomes attractive interaction. And there are different other tip sample interactions like frictions. Cantilever bends laterally due to friction force between the tip and the sample surface. Separately, this can be used in lateral force microscopy called LFM. There can be additions also. Addition can be defined as a free energy change to separate unit areas of two media from contact to infinity in vacuum or in a third medium, right? So in general, care has to be taken with the term addition since it is also used to define a force. Addition force, for an example, force modulation is used in force modulation microscopy, which is another branch of AFM. In force modulation microscopy at ambient condition, in addition to the intrinsic addition between the tip and the sample, there's another one from the capillary neck condensing between the tip and the water meniscus. So there will be interference from the humidity. The pull-off forces is considered as the addition forces, which is in the range of few nanonewton of 10 to nanonewton. So I'm not going to go into details about this addition force and a force modulation microscope in these slides. Right, so AFM imaging modes, basically we call them as contact and non-contact. In contact mode, they are now in the repulsive region. That means the distance between these tip and the sample is like very small. They are electron orbitals overlapping. They are repulsing each other. So in the contact mode, in the left side, we keep the deflection of the cantilever constant. So if you keep the deflection constant, that means you have like a constant force. Constant force means either there's no different atoms there or there's no, it's homogeneous, like not homogeneous, it's uniform. So if you encounter a step, what happens? In the contact mode, if you encounter a tip, the tip sample distance is lowered. That means the force is higher now, so cantilever deflected. If you want to keep the cantilever deflection constant, then you need to use a feedback signal to keep it constant. That means you need to maintain the distance. So if you just scan the profile of that, the contour of the tip path, then you can get an idea about the sample surface. So in the non-contact mode, we don't drag the tip over the sample. Instead, what we do, we keep it closer and we vibrate it. The tip is oscillated at a resonance frequency and the amplitude of the oscillation is kept at constant. So if we encounter, let's say, a step, then a force is higher, amplitude is changed. So the surface interactions will change the amplitude. That amplitude, the change is now detected. Feedback signal will be given to correct it to the preset value, and that change is recorded. And then that will be used to get the outline of the sample. And tapping mode is a hybrid, like it's in between contact and non-contact mode, which is very famous in AFM. It's like the most common method used in AFM imaging, because contact mode, since you keep it very close to the surface of the sample and you drag it, it's like when you scan it, there's a big chance of damaging the tip of the AFM cantilever tip. So people don't use contact mode that much. Instead, they use non-contact or tapping mode. So even though we talked about three categories like contact, non-contact, and tapping mode, we can keep the scanner at a constant height. In this mode, the spatial variation of the cantilever deflection is used directly to generate the topographic data set, because we always keep the height of the scanner fixed as it scans. Constant height mode is often used for taking atomic scale images for atomically flat surfaces, where the cantilever deflection and the variation in applied forces are small. Constant height mode is also essential for recording real-time images of changing surfaces when high scan speed is essential. And the other way is you can maintain the force constant. So in this mode, deflection of the cantilever can be used as the input to the feedback circuit, and that will move the scanner up and down in the Z direction, responding the topography by keeping the cantilever deflection constant. With the cantilever deflection held constant, the total force applied to the sample is constant. And in this mode, the image is generated from the scanner's Z motion. The scanning speed is limited by the response time of the feedback circuit, and constant force mode is generally preferred if you happen to use the contact scanning mode. Non-contact versus tapping mode, both are based on the feedback mechanism of the constant oscillation amplitude. In the non-contact mode, you usually use amplitude as 100% of the free amplitude. Now, you take the cantilever, you can calculate its resonance frequency. That is, so you let it vibrate at its resonance frequency. So it is like 100% of the free amplitude. But in the tapping mode, you reduce the vibrating amplitude and set it to 50 to 60% of the free amplitude. The tapping mode provides higher resolution with minimum sample depth, right? And most of the time, if you're using non-contact mode, you operate it as a tapping mode. So the advantage of contact mode was contact versus non-contact. Now let's imagine you have a water droplet, right? On the sample, or liquid droplet on the sample. If you try to image it using non-contact, because you maintain that distance, it will not distinguish that this water droplet is something alien. It will just image it as part of the topography of the sample. But if you go to the contact mode, because you maintain that distance, it will not be affected by the water droplet, but it will give you a good topography of the sample if you're using the contact mode. That is one advantage of using contact mode scanning in imaging the sample surface or the topology. So the comparison between three scanning modes in terms of damaging to the sample: contact mode is heavily influenced by the frictional and adhesive forces and can easily damage the sample and distort the image data. Now you can see you have a sample here. When you're dragging the sample, when you keep on dragging and there was a step, the sample was like too close, it will start dragging that step, and that will eventually, if you analyze the path, the contour of the outlining of that path of the cantilever, you will not get a good idea about the sample correct morphology. But in the non-contact mode, generally provides low resolution and can also be hampered by contaminations, like if you have like water layer that will interfere with the oscillation and will prevent it giving you the true topographical image. But in the non-contact mode, takes the advantage of two techniques above, and it eliminates the frictional forces by intermittently contacting the surface, and oscillation with sufficient amplitude will prevent the tip from being trapped by adhesive meniscus forces from the contaminant layer. So yeah, so this tapping mode will give you, now if you analyze that final image, if you have a liquid layer, the tapping mode will give you the best quality image of the sample. And not only the AFMs are used for imaging, you also can use AFM for nanolithography when you are using it under contact mode. That is, one thing is nano shaving. You have a tip here and you lower it and you can remove part of these attached micelles or attached molecules under nano shaving. Or nano grafting is you can take these incoming micelles and then you can shave it and you can let them go and attach into the sample. So these are different operations that you can use AFM other than imaging, nano shaving and nano grafting. And the lateral resolution of this AFM mainly depends on the tip sharpness. So if you just look at this, you have a conical tip, you have a sample, so your tip is going over and the movement of your tip is the contour of that, or the outlining of the tip movement is imaged. And when you image it, now this is raster scan, so you will see this is the path of the tip, right? And then let's imagine you have this is a conical tip with, it's a very sharp tip, but imagine you have a very bigger tip. In that case, what happens, it will not go closer because the tip is bigger. Instead of giving the true shape, now this is the cross section we are seeing, but if you observe it from the top, this is what you're going to see, right? This is the top of the mountain or the hill that you see in the cross section here. But here, instead of seeing the true image when you're watching from the top side, it will give you some sort of a distorted image. So if you're using a bigger tip to sample a smaller structure, the imaging will not give you a true topography, right? So let's imagine this is like in a, if you put it simple, you have a step and you're trying to profile it using a truck with a bigger tire, that will give you a distorted image. Or with this bug, like with the small tires, if you go over it, you will be getting the true shape of that step. So fat tip effect is what you call when you measure a sample with a wide tip or bigger tip. So that is the apparent width measured by using a larger tip. So this is very simple mathematics here. So you have the sample here. This is the small, let's say it's like a cylindrical one. That what we're seeing here is a cross section. So our sample is smaller compared to the our tip here, and your tip is now rolling over the sample, and we take these two instances and come up with the value for the apparent width measured by this larger tip, right? So this x is the distance between the center of the sample and center of the tip. You can easily measure it using the Pythagoras if you apply the Pythagoras equation, here you have R tip, and you can get this value here is the R tip plus R sample. Here it's the R tip, and here is the small is the R sample. And if you take this triangle, you know the R tip, you know this value, you can simply find the X. R tip plus R sample, this is the diagonal value, so you subtract R tip square with this distance, and then X square is this one, right? And this is simple Pythagoras theorem, and then you can come up with the value for X is 2 times square root R tip times R sample. But apparent width is, this is the apparent, like if you monitor the tip movement, what you'll be seeing is the movement of the center of the tip. So X is the radius from the distance from this sample center to the tip center. So you need to double it in order to get the apparent width measurement. So you can double it. So that is 4 times square root R tip times R sample. Measured with distance between the first and the last tip sample contact there. So this measured width is measured between the first contact and the last tip sample contact. And smaller the tip, that is smaller the R tip value, the smaller the measured width. And then when radius of the tip is around 1/4 of the sample, you can see the measured width is around 2 times the R radius of the sample. So if you use for 5 nanometer feature, or let's say a particle, if you use a tip apex around 1 nanometer, then you can get a reliable lateral measurement. But to get a tip apex with 1 nanometer is quite challenging. So normally the tip size is around 20 nanometer or larger. So if you try to image a 5 nanometer feature using a bigger tip, that you will see you will be getting around, like for the DNA, it's around 2 nanometer, the feature size. So tip, if you use around 10 nanometer tip, apparent width you're getting is 25 nanometers, but in reality, it's around 2 nanometers. For tip around 10 nanometer, you will be getting apparent width around 18 nanometers. You can easily do the calculations using this equation here. And another challenging thing for lateral imaging is to differentiate 2 adjacent features. Small features, they are close to each other, but if they're too close, the tip is too large, they won't be able to differentiate it. And the size of tip size on imaging resolution is what I was talking about, the lateral imaging in the previous slide. So see here, you have one feature sitting, you have the tip geometry. Even though it is distorted, it will somehow give you a distorted image. But if it is a bigger feature, like the height is greater, you will see the elongation in the image showing that it's a bit longer. But imagine you have 2 features closely situated. Instead of seeing 2 features separately, what you will see is a one big distorted image. Now imagine there's another feature sitting in between these 2, then the middle feature, because it's like too closely situated, it will not be resolved. It's just one big distorted image. So for the minimum separation for resolved asperities, the distance between these two, like the top and the bottom here, this is the blind profile. It should be at least 19% difference to get a minimum separation. So if you have a large tip for measuring features apparently larger than the real size, and larger tip cannot discern two or more adjacent features, and higher resolution demands sharper tips with very sharper tips. Sharper tips. And how to fabricate AFM tips? First, you take a silicon or silicon wafer, and you can pitch. You can etch a pit in the silicon wafer. For this etching, you can use the focused iron beam, or there are some other ways to do that. And then once you etch it, you cover the whole thing with silicon nitride coating. And then what you do, you under etch the silicon wafer underneath, leaving the cantilever and the tip. So this is a clean glass surface imaged using AFM. Even though the clean glass surface looks like it's very smooth, but in atomic scale, it has a roughness around 0.8 nanometers. These colors, they don't have colors. This is just a measurement of like atomic forces exerting on the cantilever tip, and then that is measured whether it will be given a feedback signal to either increase the height or increase the current, or a feedback signal will be generated. While doing that, the change is recorded somewhere, and that is converted to get the image. So there's no colors actually. These colors are artificially induced to get a to make it easier for the observer to get an idea about it. So lastly, this is a comparison between traditional optical microscope, electron microscope, and scanning probe microscope. For the traditional methods, we have the light and electrons I have categorized as 1 and against SPM. So in the mechanism, in traditional techniques like light and electron microscope, it uses properties of waves, right? In light, it uses a beam of light, and in electron microscopy, it uses a beam of highly accelerated electrons, which now acts as not as particles but as waves. So they use the properties of waves such as diffraction, deflection, and scattering to detect. But in the SPM, or the scanning probe microscopy class, they use a tip which scans over the sample. Mechanism is they use the interaction between the tip and the sample. It can be mechanical, it can be like it can be a force, atomic force exerting on the tip, or it can be a current, electrostatic current flowing either from tip to sample or sample to tip. Right. So in the electron microscopy, or in the traditional cases, the sample is kept under high vacuum inside a chamber, and strict sample pre-treatment is given. Usually for the TEM or SEM, we used to, if it is not conducting sample, we used to coat them. And then we put some carbon tapes or copper tapes, so that electron will not accumulate on the sample, damaging sample, but it will flow and nicely flow without accumulating. In the SPM, usually you can keep it under ambient condition. You don't need to keep it inside a high vacuum. But in the STM, we use a high vacuum system. But usually in AFM, we don't need to maintain a vacuum. Usually we keep it under ambient conditions, though high resolution imaging requires high vacuum to keep clean surface, and it's highly flexible with other techniques. Resolution, you can go down to angstrom to micron level, and it's really good to get a topographical idea and about crystallographic idea using the traditional microscope. But in the SPM, you can go down to atomic level. So far, it has the highest resolution using STM, scanning tunneling microscope. So the resolution varies between angstrom to nanometer. And this is really good for Z height measurements and good at topography imaging. SPM alone itself cannot replace electron microscopy. So these scanning probe microscopies and electron microscopies, they complement each other. We usually use both techniques depending on the situation. And SPM is not just superior in high resolution imaging, but more importantly, it can target and manipulate just one atom or one molecule at a time. So that is the most important thing in scanning probe microscopy. Right. So with this, I'm going to wind up my lecture about AFM under scanning probe microscopy. Thank you.